everyone. So recently there was a request on one of my YouTube videos for me to do a video on one of the best moments of my life. To start with, I thought it was a bit of a joke, but then when I thought about it carefully, I thought actually it could be quite a good idea for a video. So I decided to choose one from 10 years ago. It was the 2010 KU Leuven GroupT small solar vehicle competition, which I ended up winning together with my team. It's something I look back proudly on, so thought I'd do a video on what it took to win, as well as how it relates to racing in general. So first of all, if we think about what is defined as one of the best moments in someone's life, for me it's at the moment of self-realization, when I feel like I really maximized my creativity, leadership skills, and engineering skills. So if we go up the list of needs in the Maslow's triangle, from physiological, safety, belonging, esteem, and self-realization, I think we can feel lucky if we feel like we reached a point of self-realization at some point in our lives. So some of you might have seen the slide before, but it points to some of the, what for me were highlights in my life, at least professionally. And winning the small solar vehicle competition 10 years ago was definitely one of those points. If I look at how the small solar vehicles competition relates to racing in general, and what my experience taught me, is that first of all you need to be familiar with the rules of the competition. This is the case for the small solar vehicle or any other maybe real solar vehicle racing, but applies just as well to Formula SAE or any other category of racing, all the way up to Formula 1. You see Formula 1 teams looking for loopholes in the regulations all the time. You see, for example, 2009 when Braun GP won the title with Jenson Button using the double diffuser. It's a very good example of that. So you need to get familiar with the rules of the competition, look for any potential loopholes. You should learn what you can from successful teams, successful cars from previous years. Properly engineer your vehicle. There's no way around this, of course. And use creativity to look for an unfair advantage. So, for example, in Braun GP's case, it was a double diffuser. It can be something else in whatever competition you're taking part in, but really get familiar with the rules and try and see if you can find a loophole somewhere. Then you must test your car before the competition to improve reliability. To win first, you have to finish. If you can, try to psych out your competition. This is not always possible, and of course, first of all, you have to concentrate on yourself, but if you can, try to psych out the competition. That is also the case in other competitions, whether that's tennis, chess, or anything else where there's a competitive element. Specifically for racing, you should design your car for easy setup changes and adapt your car setup to the racing conditions. So all of this applies no matter what type of car racing you're doing. Oh, and tire wraps and tape are always handy. If we look at the rules of this 2010 small solar vehicle competition, each team received identical solar panels weighing roughly 360 grams in February or March. I think it was around February, and the competition would take place in May. The goal of the competition was to jump as far as possible into a box of foam after driving up a 14-meter long ramp, which was inclined at 3 degrees. And this entire run had to be completed in less than 20 seconds. Each team was free in design of the solar vehicle as long as the minimum weight stayed above 500 grams. And as the solar panel itself already weighed 360 grams, that only left 140 grams remaining. So once you add the weight of the motor and wheels, everything else, actually the 500 gram limit was quite difficult to reach. We looked at some designs from previous years, and what we learned was that, first of all, mini DVDs and mini CDs could be used as wheels. The minimum weight was actually quite hard to reach. A previous winner actually used carbon fiber sheets to create the body, and the motors from a company called Maxon in Switzerland seemed to be the way to go. So in engineering our vehicle, the process we took was to first measure our given solar panel, sorry, not in December, but in February, under known irradiance. So irradiance, that's the amount of power per given area in the sunlight. So we then looked up the solar irradiance data to extrapolate what it would be in May. We then chose a motor based on the extrapolated solar panel output. We worked out the optimized gearing in Excel based on formulas formulas of equations of motion. So if I show, so this was our engineering report from the time. You can see, first of all, we made some measurements on the solar panel based on what is known as a diode, a diode factor M. So that's what we were trying to work out, and then based on some known parameters of the panel, so the known performance at say 1000 watts per square meter, and then knowing the irradiance of Leuven, which is where the competition took place. We looked up the solar irradiance for Leuven in May, so then we could see, okay, in a very good day, right at noon, we'd reach roughly 1000 watts per square meter. But then, being more realistic, and especially as the competition would last most likely the entire afternoon, the more realistic irradiance value to use was going to be somewhat lower. So I think we settled on like 600 to 700 watts per square meter. So then, based on that, we worked out say the maximum power output of our panel. We then looked into what would be the optimum motor to use given the extrapolated performance from the solar panel, because there were different motors that we could choose. And so if I look here, so yeah, we worked out what would be for the panel. Then for the motors, we basically chose from the catalog of Maxon quite a few different ones. The main difference was that they went up in different ohms, and I think in general, if I remember correctly, it was like, so I believe the higher our expected power, then the lower the motor resistance should be. Okay, it's been 10 years, it's a little bit fuzzy now, but from what I remember, that was the case. Okay, that seems to be correct. So if I look here, it seems like for the motor with a very low resistance, it was optimized in efficiency for high power, whereas the motors with a high resistance were more optimized for low power. So based on what we expected as a power output of the solar panel in May, we then picked this particular motor, the Maxon RE Max 5 watt 9 volt, with a coil resistance of 2.2 ohms, and we worked out that it was going to be fairly efficient over a wide range of expected irradiance range that we were most likely going to see. Based on that, we then worked out, Psyching diagram where all the energy is going. We then worked on optimizing the gear transmission ratio. So we did that by writing down some formulas, equations of motion, rotational inertia, the slope of the ramp, coefficient of rolling resistance, things like this, because the main point was to losses through the gears. The main point was to try and work out what is the optimum gear ratio to reach the maximum jump speed at the end of the 14-meter ramp, and that was done using this Excel. So we worked out, for example, for each particular motor, what the target RPM at which the maximum power would be developed, for example, and then so with a whole bunch of formulas, in the end we worked out. So distance 14, that's the ramp, length of the ramp, and in the end, by playing around with this K value, which was the transmission ratio divided by the radius of the wheel, it was basically playing around with this until the acceleration distance equaled 14. That meant that we would get to the optimum speed at the end of the ramp. So with that, we knew roughly what the optimized transmission ratio would be for a given motor, for a given irradiance. So then from that we could work out, what is the number of teeth that should be on the pinion on the motor, what should be the number of teeth on the shaft. So that's the engineering done. So then we could tell that the time to finish was actually only around 5 seconds, depending on conditions and so on. One other thing. So in this case, what we were working on was to maximize the final speed at 14 meters, because we want to jump as far as possible. Had we optimized it for race time, we would have gone for a different transmission ratio. It would have been a lower transmission ratio. So in real circuit racing, you're doing this kind of trade-off as well. So if you're in real circuit racing, it's not the speed at the end of the straight which counts. It's actually how fast you go over the entire straight. And so that in such a case, actually, you want to accelerate quickly. So then using a higher gear ratio can actually be beneficial to, can actually work out better than having the highest speed at the end of the straight at the speed track. So that's just a side note. Okay, let's get back. So finding an unfair advantage. So we saw that the time to go up the slope was only about 5 seconds, and the competition was in essence about turning solar energy into kinetic energy. So according to our calculations, we had about 15 seconds of solar energy that we were not using. So what did that mean? So the answer was to an unfair advantage would be if we could store that additional 10 to 15 seconds of solar energy and put it in the ultracapacitor, and then turn that into kinetic energy as well. We needed a switch circuit. So first of all, we would charge the ultracapacitor for about 10 to 15 seconds. In the charging circuit, the motor would be omitted, and the panel is then charging the ultracapacitor. And then there would be a driving circuit, so release the switch, the panel and ultracapacitor would power the motor in parallel. Oh, okay. So we did some testing refinements. To start with, we had quite a long wheelbase. The wheels were fixed to a shaft, so glued physically to a shaft. It's a bit like having a lock differential or just solid axle. We had quite a long wheelbase. Running on flat ground worked quite well. Tracked very straight. Issue is when we tried this when we tried the vehicle with a long wheelbase on the ramp, it didn't work well at all. So the nose would just drop immediately into the foam pit. So we needed shorter wheelbase. So in the in the whole process of optimization, we tried to reduce the rotating mass. So actually we probably went a bit overboard on this point, but what we ended up doing was actually have fixed axle and have the wheels rotating freely on the axle rather than having the axle rotate with it. So whereas in the first iteration, we had these bearings glued to the frame, and then a shaft running through the bearings, which were glued to the wheels, and therefore having the wheels in essence having a lock differential in between. What we ended up going to was having the shaft became part of the frame in order to reduce weight and also reduce rotating mass, and then the wheels were then rotating on the bearings, and so that minimized the rotating mass. The problem was then it's like you have in essence you had like an open differential, which means the car becomes a lot less stable. So we moved to two freely rotating front wheels and a single driven rear wheel. So with the very short wheelbase, this did not immediately dive into the foam pit. That was good, but and it had less rotational inertia, but it was a lot less stable. So we had to add some guides on the frame to prevent the solar vehicle just veering off course. This is actually quite similar to something you see in real cars. If you have a fixed axle or completely locked differential, then that really has a very stabilizing effect on the vehicle. But it also means that, for example, you end up with a lot more understeer at turn-in. So if you ever move from, say, an open differential vehicle, rear-wheel drive car, and you add a locking differential in between to improve traction, you might notice that if you go overboard on the differential lock, you will have a lot more turn-in understeer. So, psyching out the competition. So I don't know if this worked at all, but we certainly did get some surprise looks from the other teams when we showed up with our solar vehicle with wings attached, because there was nothing in the rules saying that you cannot attach wings to your small solar vehicle. So unfortunately, our vehicle wasn't driving fast enough to really make use of the wings. But anyway, the wings certainly didn't hurt too much in the beginning, and in the end we removed it, but by the time we removed it, it had served its purpose. It had certainly, probably psyched out the competition. Finally, during the competition itself, so as mentioned, the sun was, the angle of the sun was changing, because it started around noon, but then by the time we finished, I think it was around 4 p.m. So the sun was moving, and then ideally you want to track the angle of the sun. So as you can see here on the left, the panel was just completely straight, because the sun was straight ahead. The panel was simply angled slightly up slightly upwards to catch the sun's rays. But towards the afternoon, as you can see from the shadows, the sun had moved very much to the right. So we made sure to angle the panel towards the right to catch the sun at the optimum angle as much as possible. And it was possible because we used glue gun whenever we need to make repairs, and to angle the although the panel was a structural component of our vehicle, in this case we just stuck a piece of foam in between the frame and the panel and tied it down using tie straps. And I must say at the time it was very much I was really nervous because before and really relieved when we won, because before the competition started, I said, we will definitely win. I was telling my girlfriend at the time, my wife now. So I was telling my wife, my mom, my cousin, that we'll win. We will win. We will definitely win. But as the day got closer, I wasn't so sure, because what I thought would be an unfair advantage, I thought, maybe all the 150 other students, surely someone's bound to think of it. But as it turned out, no one did. But no one did, and we actually managed to win quite easily. So if I zoom into here, so we were team 70. You can see the distances written on the screen. So we won with a winning jump of 123 centimeters, but all throughout the competition we were always around the 120 plus. So in the final 123, semi-final 127, and then before that 138, 126. So I think thanks to the ultracapacitors, our performance stayed quite consistent, even though the angle of the sun was changing. So I think in terms of gearing, we were probably more on the conservative side. So in the early rounds, had we chosen a bigger a different gearing ratio, so bigger pinion on the motor, we probably could have jumped even further, but then it would have been too big for later in the afternoon. And as we already had quite a comfortable margin over the competition, we decided we didn't change the pinion gear. So we had a set of different gears on the day between which we could switch, so we could observe whether it was running properly, and we could reduce or increase the gearing if needed. But in the end, we once we had one which was working quite well, we just stuck to it as and mainly worked on the angle of the panel. I have a few small videos. So this was early on in the competition. Let me show that again, sorry. So here you can see very much early on, with the wing, it dived into the panel, into the pit a lot further than the competition there. This was, I'll go forward a bit. So early on in the competition, the organizers didn't really catch on to the fact that we were charging our small solar car before releasing. So then, in fact, we could charge it for a lot longer. But towards the end, everybody caught on, and they were making sure that the ultra capacitor was completely empty before the 20 seconds. So this is what you see is happening here. The organizers, they were making sure using so our solar vehicle is flipped over, the panel is completely covered, and they're measuring using multimeter to make sure that all the power has been drained from the ultracapacitor. Once the competition starts, so here's the competition's about to start. So you see the other team has already released it. Okay, I don't understand. I don't understand why that guy tried. Made a jump again, but the difference was that I'm for the first 10 seconds or so I'm just charging up our vehicle, and then once I release it, you can see that clearly it's running a bit faster than the other vehicle. That's it. Hope you enjoyed the video, and so remember if no matter what kind of racing you're doing, get familiar with the rules. Learn what you can from previous successful cars. Properly engineer. Look for unfair advantage. Test before your competition to improve reliability. Psych out your competition if possible. Design your car for easy setup changes, and set up your car for the racing conditions. And keep some tire wraps and tape handy. They are always useful.